Way to go.
Alright, antiderivative.
Also known as what?
A function. It's called capital F. Is an antiderivative of F and we'll give the True Books definition here. I could probably summarize it a little bit shorter, but a function, capital F, is an antiderivative of F on an interval, we'll just call it interval I, if capital F prime of x equals just lowercase f of x for all x on the interval I.
Is that 4?
4, yep. I don't know what happened to the...
Oh, is that because, like, when you're finding the individual, since it's going to be one, or no, that's, never mind. Never mind, I answered my own question.
Sure.
So is capital X is in it?
Okay. Basically what it's saying is the function capital F is the antiderivative of lowercase f if, when you do the derivative of capital F, you'll get lowercase f.
Okay.
Can I follow that? Just get a quick little summary there. Okay? Antiderivatives are notated f of x plus c, where c could be any constant. Let me give you an example of what I mean there. Okay.
Then how was the normal derivative notated, or did it not have its equivalent of that?
I think this will answer it. Everybody got this? Okay. So let's say that in this case f of x is 2x.
Okay.
Okay? So that means then the antiderivative, again I'm using capital F to represent the antiderivative. The antiderivative of this would be x squared plus any number, plus any constant.
Right.
Okay? So that could mean you have x squared plus 1, x squared minus 6, x squared plus 8, okay? All of those would be antiderivatives of this, because what do you get if you take the derivative of x squared plus 1?
2x.
2x. What do you get if you take the derivative of x squared minus 6?
2x.
2x, okay? No matter what. So that's why we will notate, when you guys are doing antiderivatives, you'll always put this plus c back there, unless they give you some initial conditions, because any constant could be back here on the antiderivative, and the derivative of this would give you this no matter what, because what's the derivative of all constants? 0. Okay, the derivative of 5 is 0, the derivative of negative 6 is 0. So that's why you'll want to remember to put plus c when you're finding the antiderivative of a particular function. Okay? Thoughts? Yes, no? Okay?
What if we had to do it more than once? Or like, okay, so you know, like, if we were working the other way with something that had x squared plus x plus c, let's just say, we'd know. I'll think of a better way of explaining my question and then
Okay.
ask.
Alright, yeah, I'll let you think of a better way. I think I know where you're going with it, but I don't wanna say anything. So, anyway, that's what I mean by antiderivatives are gonna be notated f of x plus c. So if they ask you to find the antiderivative of the function, just remember to put plus c on the back end of it, because the antiderivative of a given function could have some constant on the back end of it. You don't know what that constant is, you don't know if that constant is even there, but you need to put it there to represent all possible antiderivatives. Okay? So that one was pretty self-explanatory. Let's say I gave you another one. This one would be pretty simple as well. So let's say f of x equals cosine of x. What is the antiderivative of f of x?
Sin x.
X plus.
Negative
sine
plus c.
C.
The antiderivative of that would be sine x plus c. Because if I asked you to take the derivative of this,
It would get
sine of x plus some number, plus 7, whatever, okay? The derivative of sine x plus 7 would simply be cosine x. Okay? You're working backwards. How can you check your answer? Take the derivative of your answer. You know, if this is what you think the antiderivative is, okay, take the derivative of your antiderivative and make sure you get what you're supposed to right there. That's the way to check to see that you did the antiderivative correct. That making sense? Okay. All right. More notation. Notation for antiderivatives slash indefinite integrals. That kind of crazy S-looking symbol as an integral sign.
And that's the same as antiderivative?
Yes. Integral sign. If you see an integral sign, it is asking you to find the antiderivative. Okay? This is asking you to find the antiderivative of this function in terms of x. To do the antiderivative in terms of the variable x. Most of them here at the beginning, everything is going to be in terms of x anyway, so there's nothing really new or different going on there. Okay? So this is called the integral sign, and if you see this, the integral of f of x dx, it basically means to find the antiderivative of f of x with respect to x.
If it was over something, would it be respect to x, but also having that other variable in it? Sort of like when we were doing it the other way, or would it be? Because wasn't it d of x over d of y, but since d of y was usually 1, that's why we didn't have to? Or am I forgetting something?
I don't think you're going to have an integral of something over something per se.
But wasn't our notation when we were finding the derivatives dx over dy, and then dy equals 1, so it was just written as dx in the beginning?
I think so, yeah, it seems to make sense.
So what I was,
If it shows up, great, if not, don't worry about it, okay? So, f of x is the function that you're gonna do the antiderivative of, okay? It's also called the integrand. I'm not gonna use that term a bunch, but officially it's called the integrand. So what you're going to take the integral of or the antiderivative of. And dx is simply the variable, again, you are doing the antiderivative with respect to, okay? So that's all that really means there, okay? Antiderivatives is the same thing as doing indefinite integrals. Indefinite integrals. They're the same terminology-wise, okay? So if I say, what's the indefinite integral of this? It's just like me saying, what is the antiderivative of this, okay? The definite integral, that gets to be something different, okay? The definite integral is where you actually use this to find the area under the curve, instead of doing all the real sums.
So will we get there eventually?
Yep, we're not too far away. Okay? Want to write this down as well.
so isn't that like a simplified version of what we wrote up above, basically?
Kind of put them together. This is basically saying that integration and differentiation are inverses of each other. They undo one another.
Sort of like multiplying versus dividing.
Correct, yeah. The integral, or the antiderivative of the derivative, would equal just the function itself. Does that make sense?
Yes.
If you would do the derivative of a function and then do the antiderivative of that function, you'd get the function itself, right? Plus some constant potentially. All right, you don't know. All right? And the opposite would also be true if you took the derivative of the integral if you took the derivative of the integral, or the derivative of the antiderivative, you'd get the function itself. Okay?
What did you say d of x was equal to?
This is just the variable you are doing the antiderivative with respect to.
Okay.
Do you remember how we had to at some point do implicit differentiation, first chapter with the dy dx, anytime you saw a y within the function? You didn't have to do that until there were both y's and x's within the function. For starters, you're just going to have x's in the function, so it's just the variable you're differentiating or doing the antiderivative with respect to.
Okay.
Okay? Okay. All right. This is just showing you integration, differentiation, they undo one another. They're opposite operations like multiplication, division, like addition, subtraction, like squaring and square root. Okay? They undo one another. So, let's see if we can do some of these. We'll do some examples together. What is the integral of 6x dx? So the antiderivative of 6x dx.
6x squared?
Nope, because if
No,
I did
it
the
would be-
derivative of 6x squared, I would get 12x.
3x squared,
3x squared? Alright?
right?
I have no idea.
Plus c.
Plus C.
Okay.
Plus C.
Plus c. Yep.
Oh, plus c.
Alright. Now,
Oops.
this is.
Sorry.
So,
It's a little crooked. Sorry.
Someone's gonna be watching that.
alright. You know that when you do a derivative, you a lot of times use the power rule, right?
Yes.
So the power decreases by 1, right? Like if you had 10x to the fourth, you take the 4 times the 10, which would be 40, and then your x is raised to 1 less power, right? Okay? Well, this is like, we've done the derivative already. What's the power on the x right here? 1. So what's the power on the x going to have to be in the antiderivative? 2. You're going to have an x squared in it, right?
And then you have to divide.
So you
the
kind of
6 by 2.
already know you're going to have an x squared in it, but then you could think, well, it can't just be x squared, because if I did the derivative of x squared, I would just get 2x, right? Well, I need to somehow get 6x. So I need to think, when I do the derivative of this, 2 times what is going to give me the 6 that I need right there? 3, okay? So 3x squared, don't forget your plus c
So
at
you
the
like
back end.
adding a exponent instead of subtracting?
When you're using the power rule, yes.
And then would
Yep.
you divide whatever the coefficient is by what you find it's supposed to be?
Divide the coefficient by the power
That it's going to end up being.
that it's going, so by n plus 1,
Yeah.
if you will. Okay? Is that your rule of, how do you, let me see how you write that out. I always just think backwards.
So this is the only way to do this, is just work backwards?
Yes.
I'm alright with that, this is my kind of stuff.
Good.
You know,
Sit down, think
stuff that I
about
don't
it,
have
sit
to,
about
you
it.
know,
That's what he
Steel trap.
this is what
This
I
is the
thrive on.
steel trap kind of stuff.
I'm going to use x's instead of t's just to not goof people up here, but
That way I can go into the test, I'm prepared, and just sit there and figure it out.
Seems like maybe it's not that strategy.
That's what I did all last semester, argue with my A minus
X to the n plus 1. Oh, I love this song.
Oh,
so in general, there's kind of a
There it is.
formula for finding the integral.
That's not terribly bad.
So just work backwards.
I think just work backwards, how I've always done it. But Bailey uses this, she likes using it, it works for her, so
So you don't need to practice.
no. No.
Probably not good.
Okay?
It's a big formula, but it helps in physics a lot.
Good thing this is.
Because the numbers aren't always very nice, and you can't automatically just think, but you can figure it out by dividing. Absolutely, you can figure it out by dividing.
All right.
Okay. So I'm going to give you a couple more, just really basic ones here. Okay?
Got it.
I'll let-
We good?
Okay?
You mean I'm gonna get harder than this?
So 2/3 x squared.
I'm thinking way too quick. It's definitely.
Or no, it would be
It's definitely
2/4,
to the
which is
fourth.
half.
Okay. Can't forget
Gotta
that.
have that.
What if you didn't have it? You just
Way
would
too
know
early.
your respect to X, but whatever. Why do you start from the bottom? Go up. With the little squiggles.
Can you check mine?
Why do I start?
Yeah, why do you go from there and not from the top?
Was I?
Yeah.
On all of
got
Yeah.
X squared.
yeah,
Yeah.
I noticed that too.
I did.
Yeah.
Yeah, you got, yeah. I can do it too,
Do you have one?
No, that was bad. I can't do that.
I'm trying to perfect it now. It bugs me that you do it that way.
And they look so awesome.
You obviously had your
Oh, no.
fair share of practice.
Maybe just a few
Plus
times.
Yeah.
Yes.
So this is definitely next to the four.
Is that it?
The great thing about these guys is you did a whole semester worth of derivatives. So,
We're doing the whole
once,
semester of the
basically, yeah. Once you think you have your answer, do the derivative of your answer
Oh, duh.
to check,
Ha.
to make sure you're right.
Ha.
I have a,
Yep, that's good.
if you wanna argue with me.
That's...
So it's hours studied plus pages of
Put
notes
some
of the
new
grade
shoes
point
on.
class.
Everything's right.
And the key is you wanna get a,
Okay, we'll do
very
it.
key.
Okay, so my thought process on this my thought process on this would be, okay, I know I gotta have x to the fourth. Okay, again, I'm not using the formula, alright? But I know I have to have x to the fourth. Well, because I know I have to have x to the fourth, I'm going to take the 4 times whatever is here, and that'll give me x to the third. So 4 times something has to equal 2. 4 times a half, right?
The goal is you want to get
So 1/2 x to the fourth plus c. Okay, let's see if I'm right. What's 4 times a half? 2. X to the 1 less power, so that'd be 2x to the third. Ding, 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 got it right. That's kind of my process that I take. Okay?
I get used to grading plus C.
So this one. I know I have to have x to the sixth. 6 times something has to give me 4.
Why not just take 4 divided
2.
by?
I'm just talking through my thought process here.
Oh, okay.
There's that, and there's lots of different ways.
Okay, I'm sorry.
No.
He's gonna take 4 divided by 6, which is
Justin,
simple.
check.
He's going to take this,
check.
divided by the power, that's 1 higher than what you have. Which is the same thing as me thinking 1 times the higher power what I have times what gives me this. I do better thinking multiplication wise. This one's pretty easy either way. So 2/3 x to the sixth plus c.
I need to stop forgetting the plus C.
Oh, shit.
Okay? I know that has to be x to the third. I need a -3. So 3 times what gives me -3? -1. X to the third.
Why write the
Can you just
line?
make it negative x to the third?
Negative x to the third plus c. Yep.
Go. No.
Okay?
What do you want you to do?
Just quick thing. If that were a squared, would we want to